Welcome back, everybody. I want to talk about the other common forces today: normal force, tension, and the force of friction. Normal force we talked about a little bit last chapter already. Normal force always acts perpendicular to a surface. That's actually why it's called the normal force, normal mathematical term for perpendicular. It's equal to the force that the surface must provide to prevent an object from passing through the surface. We talked a little bit about last chapter, the fact that every single surface is a bit of a spring. And the larger the force you apply to it, the more it bends, and the larger the normal force it applies. How does it actually do this? Mostly, if you try to put your finger through the table, it's because the electrons in the table repel the electrons in your finger. That in itself is not too large, but you still won't be able to put your finger through simply because of the Pauli exclusion principle, that the electrons in your finger can't occupy the same space as the electrons in the table, which prevents most of it. Normal force, unfortunately, is usually abbreviated with a capital N, which is the same as the abbreviation for the unit of force. Please don't let that confuse you. Tension is the force exerted by the end of a taut cord, a string, a chain, a support, a wire, any other kind of towing device, and it's called tension. The tension is always the same throughout the entire length of the cable and equal to the force or tension exerted at the opposite ends of the cable. Unlike normal force, tension is always parallel to the cable or acts along the cable. Some quick examples here. And this is the bizarre part, that idea that tension is the same no matter what part of the cable you're talking about. Olympic week, sometimes we have different classes compete against each other with tug of war. Usually the upperclassmen win over the underclassmen, but not always. But my question is if you've got a team winning, for example here, that the left-hand team is winning and pulling the right-hand team over, which one of these tensions is larger? So imagine, they're accelerating towards the left-hand side of the screen. Is this tension larger or smaller than this tension? And the answer is, strangely enough, they're the same. The tension on the left is the same as the tension on the right, even if the left team is winning. So you're wait a second. If tensions are always the same, how can anyone win a tug of war? And the answer is, believe it or not, it's not the tension in the rope that's the critical part. It's a little bit of strength, but the primary part of this thing is actually the friction between the feet and the floor. Sorry, pushing my button by accident here. In this case, the friction which prevents them sliding, let's say this is the upperclassmen team, is larger than the force of friction between the opposing team. And if this is larger than this team is going to accelerate this way. And if this is larger than this team is also going to accelerate backwards. So the tensions in a rope are always the same at every single point. And we talked a little bit about this, but we talked about the force of gravity on different masses. You know what the force of gravity on this one is going to be 9.81 newtons. Why is this mass not falling downward? Because the tension in this cable has to also be 9.81 newtons. What happens if you put a pulley in, like in your lab? We talked about this before. The tension is still the same at this point right here. The tension still must be 9.8 newtons going this way, so that this thing stays in place. The pulley just redirects the tension without changing it. So again, we still have that 9.81 newtons acting downward. Why is the mass not falling? The string is still providing it at every single point, here and here and here. And now here's the one that trips up everybody. And I wish I was here so I could actually pause and ask you this question, but I'll ask you anyway, and whoever my sub is, I can actually kind of see the results. My question is this. If you've got 9.81 newtons, you got two 1 kilogram masses held by pulleys over here. What's the tension at this point in the cable right here? Let me give you options. A, 0 newtons. Why? Because the two forces cancel out. B, it's still 9.81 newtons. Mr. Clomber, what are you talking about? Or C, 19.6 newtons. the sum of the two tensions required. All right, pause the video for a quick second. Choose your answer before I give the answer. If you want to do a class poll, you can if you're watching this all together. Correct answer is not 0 newtons. No, there is a tension in the rope. Leaving us these two choices, and believe it or not, the answer is not 19.6. If you chose 9.81, you're absolutely correct. And you might say, whoa, wait a second. This is so different than this previous one because, there's two masses. Well, in reality here, what's happening here, the wall is exerting a tension as well to try to hold this whole thing in place. All we've done in this case is replace the wall with a mass that's exerting that same 9.8 newtons. The tension at this point is simply 9.81 newtons. Why? The tension's the same at every single point. What's the tension here? Oh, 9.81 newtons. What's the tension here? Oh, 9.81 newtons. What's the tension here? Same part, same string, 9.81 newtons. Moving on. Oops. Friction is probably one of the more challenging parts in this chapter, and don't panic real quick. The first thing I need to tell you is that there's two different types. Static friction, which we usually represent as F sub S, friction, static, is a force of friction between two stationary surfaces, static surfaces. It can range all the way between 0, this is the force static friction, up to a maximum value, and this is the Greek letter mu. Mu sub S times the normal force. Mu sub S is called the coefficient of static friction. And you might say, whoa, what's going on here? Well, think about for a quick example. Imagine you've got your book sitting on the tabletop in front of you, or your laptop. Laptop's sitting there stationary, if you apply a small force over here trying to pull it over, what's going to happen? If that force is small enough, it won't move. Why? Because the force of static friction is going to exactly match it. And you can keep making this larger and larger and larger until at some point it'll become large enough that you'll exceed the maximum value that the force of static friction can be. That's this product right here, at which point it begins sliding. What happens if you don't apply a force to your laptop and it's on a level table? Well, then the force of friction, static friction, is actually 0. It's actually equal to the 0 point over here. So static friction is kind of interesting. Now, the interesting part is once you do have it sliding, I got to draw my picture here. Once your laptop is sliding, now the value of friction only has one value. So if it's moving this way, the force of friction, which we now use the term kinetic friction, just has one value. The force of kinetic friction is the force of friction between two moving surfaces, and its value is just the coefficient of kinetic friction times normal force. This, again, the Greek letter mu represents the coefficient of friction, sub k, the kinetic part, and F sub k, the friction kinetic, or kinetic friction. Now you might say, well, wait, how do I figure out what this mu sub S and mu sub k is? The coefficient of static friction and the coefficient of kinetic friction. And the answer is, it's pretty doggone easy. There's tables of this published. If you go over to Mr. Beckman's room, you'll find the Handbook of Physics and Chemistry. It's this huge, thick book. It's about 20 centimeters thick, and it has pages upon pages of every single possible mu sub S and mu sub k for just about everything ridiculous you can think of. For example, you'll find diamond on diamond, dry. Diamond on diamond, lubricated with mineral oil. Diamond on diamond, lubricated with WD-30. Diamond on diamond, lubricated with whale oil. A little strange. Diamond on diamond, lubricated with linseed oil. Diamond on diamond, lubricated with flaxseed oil. And yes, it goes on for pages and pages. And once you figure out diamond on diamond, then it goes diamond on ruby, diamond on sapphire, and on and on. My strangest entry I've ever found in the book is leather on horn. You're like, horn? Yeah, like reindeer horn. leather sliding across reindeer horn. Yes, there's a mu sub s and a mu sub k for that, and you can find it in that book. But anyway, this table I have in front of you gives you some quick examples. So steel on steel dry gives you mu sub s and mu sub k. Notice that mu sub k is typically smaller than mu sub s for most materials. Once you're sliding, there's less friction than when you're stationary. Rubber on concrete, so like tires on a road, static, kinetic. Rubber on concrete, wet. Notice the huge drop, which is why you have to be much more careful driving on wet roads than on dry roads. Wood on wood depends a lot on the type of wood. Glass on glass, Teflon on Teflon. One of my favorite ones to point out here, though, is your joints. Your joints have incredibly small coefficients of friction, both kinetic and static. Believe it or not, biological systems like our joints are so well made that we have almost no friction in them unless you damage them in some ways. Later in this chapter, we'll spend a lot of time on friction, but for now, I just need you to know that it's possible to calculate it. Very rough surfaces, you can get up to mu sub k's of up to like 1.5, but typically that's about as large as you can get. One is sort of the one we sort of think about, rubber on dry concrete. That's a pretty tough thing to slide. Moving on. If you take a look at worksheet 1 in the packet, which hopefully you have at this point, there's a bunch of sample problems where you're drawing all of the forces acting on these objects. And again, it's some combination of the 4 forces we're talking about. So take a look at these, and I just want to quickly run through a couple of them with you. So in the first case, it's an object sitting stationary on the surface. What are the forces acting on it? Whoops, that's a little messy. Force of gravity acting downward, of course. And what's preventing it from going through the surface? An equal normal force acting up this way. Whoops, dinky, 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 dink. What about this one over here? You've got a string holding it up, and this is supposed to be a rooftop. What's acting on it? Again, the force of gravity. And in this case, the tension acting upward. This time we're dealing with tension. And yes, I realize that tension's also pulling down on the roof up here, but we're only going to draw the forces on our object. And now here's one of the tricky ones. If you remember from last time's lecture, we talked about the idea that it doesn't require a force to have an object in motion. If something's moving under constant velocity, it means that the sum of all the forces on it must be 0. If it wasn't 0, then it'd be accelerating. In this case, what are the forces acting on it? Again, just the force of gravity and the normal force. And again, these are equal and opposite to each other. The forces acting here are exactly the same as acting here on the stationary surface, even though it's sliding across the ground. Take a look at these next set. Oh, sorry, I actually put them in here. Oh, okay. Sorry, it's going to be a little messy. All right. What about something riding on an inclined plane? Again, we have to do a little bit of work. We know that there's a force of gravity acting on it. And the question is how do we work with it? So for things on inclined planes, we're going to do things just a little bit more or differently. The normal force up there is not equal to the force of gravity. What is it equal to? Oh, in this case, it's stationary. What must be true here? The force here, let me pause for a brief moment. When we're working with things on an inclined plane, we don't break our vectors into components that are horizontal and vertical. We break them into components that are parallel and perpendicular to the ramp. Why? If we do it that way, we don't have to break this into components, we don't have to break this into components, we just have to break the force of gravity into components. And I probably should prove this to you, but the angle that the ramp makes with the ground down here is exactly equal to this angle up here inside of this triangle. And yes, this is a right triangle right there. What do we know must be true if this thing is stationary? If something's stationary or moving at a constant velocity, we know the sum of the forces must be 0. In other words, the sum of these 3 vectors must add up to 0. That means this component trying to draw it down the ramp must be exactly equal to the force of friction acting this way, so that these two components that are acting parallel to the ramp cancel out. And this component right here that's perpendicular to the ramp must be exactly equal to the normal force right here, so that these two components that are perpendicular to the ramp also cancel out, so the net force is 0. What about these? So these are just sort of some qualitative problems. You've got a ramp an object accelerating down a ramp, which means I assume it doesn't have any friction. The normal force is going to be acting perpendicular to the surface, sort of like what I've drawn here, but its magnitude should be smaller than the force of gravity. Why? The normal force is just equal to this component of the force of gravity. This piece right here is equal to this piece here. And so this is going to be a little smaller than the force of gravity. It's in the right angle there. Same thing's going to happen here. If this thing's stationary on the surface, we've got the normal force acting perpendicular to the surface, which I didn't draw very well. And if it's not sliding, there must be a force of friction acting this way. And because it's not sliding, it would be a static friction. And again, you could figure out the magnitude of these two by breaking this into components that are perpendicular and parallel to the ramp, which I'm not doing a very good job of. What about this one here? There's two chunks of wood holding it here. It's not friction holding it up here. It's actually a normal force between this piece of wood, this surface right here, and the block. And then there's another normal force between this surface acting this way. To distinguish these two, just so we know that they're not actually the same magnitude, I'll call that one normal force 1 and this one normal force 2. How do you figure out their magnitude? Again, if you broke this one into components that are perpendicular and parallel, this would be equal to this, and this one would be equal to this. Not that you have to draw those on your actual diagrams. Oh, I did draw them on here, sorry. So what about the mathematics involved? What if you actually had to solve for the various forces? Well, again, it's not too bad. Take a quick look. If this thing is angled at 35 degrees, we know that this vector, or if we make this little triangle here, we break this into its vertical and horizontal parts. Do draw your arrows. This angle up here would be 35 degrees. And grabbing your handy dandy Inspire, if this is a 7 kilogram object, the force of gravity on it, just 7 times 9.81. Sorry, give me a moment. Is roughly 68.7 newtons. To figure out this side of this triangle, we just have to multiply that by the cosine of 35. Doing that very quickly, sorry, my apologies for the slight delay. We end up finding out that this side is 56.3 newtons. And that means that this normal force here also has to be 56.3 newtons. How do we figure out this side? This side's just going to be that 68.7 times the sine of 35 degrees. And if you solve that very quickly, you'll end up with 39.4 newtons. And we know then that this force of static friction must also be 39.4 newtons. Some of you might say, oh, wait a second, we know the normal force and we know the force of static friction. Can we go ahead and calculate mu sub s? The answer is we can't. Because we don't know if this is the maximum value. Remember again, the force of static friction is always less than or equal to this value, but we don't know if it's exactly equal to it in this case. Are you okay? Good. Moving forward. What about this one? In this case, you've got a 10 kilogram mass. Again, the force of gravity on that one, that's easy to do, is 98.1 newtons. And you've got two ropes holding it in place. The question is, what are the forces acting on these? So we've got the 98 newtons I drew here. We've got the two tensions, T1 and T2. We know that some of these must add up to 0 if this thing's staying stationary or moving at a constant velocity. If we break this into its two components, we know that the vertical component here has to be 98 newtons. Why? That's the only other vertical vector besides this one, and they have to add up to 0. And if this is a 45, 45, 90, what do we know this side has to be immediately? We know that also has to be 98 newtons, which means T2 over here also has to be 98 newtons. Why? This horizontal vector is acting this way. For the sum of the vectors to be 0, this has to be 98 newtons as well on that side. And yes, you could also calculate T1 over here. It's about 141 newtons if you just figure out the Pythagorean theorem on that one. Oh, actually, 139. Sorry, my bad. Moving on. It gets a little bit more complex when you've got multiple angles and multiple degrees, but the same process happens here. We draw those two vectors, break them into their components. We know that the sum of these three vectors must add up to be 0. We can figure out the two sides of these, and now we can write some equations, and I hope I've got it on here. What do we know has to be true? The sum of these two vertical components have to add up to 98. In this case, each one's not 98. They're both acting vertically upward, and the sum of them must be equal to the 98 that's going downward. And what else do we know? That these two horizontal pieces must be equal to each other. And sometimes I drew it this way. You can also just write it this way. You can simply say, all right, this one is equal in magnitude to that one. I'll drop out the equal 0. This one has to be exactly equal to this vector over here. Even though they don't look like it on the diagram, those are the only two horizontal vectors, and you cancel them out. How do you solve these two? Go ahead and plug them into your Inspire. You can do menu 371 for simultaneous equations, and you can very quickly calculate the two tensions. Cool. Sorry, I'm writing it that way. Now, worksheet 2, I just want to go through two sample problems with you very quickly. The question is here is, given these forces, how do you actually solve them? So first thing I'm going to do is break this into its vertical and horizontal components. And you might say, whoa, Mr. Clymer, the other time you broke it on the other side of it. It doesn't matter if I do it over here or if I do it over there. I'm just putting them here because it's easy to see the 25 degrees, which means this side of this triangle is going to be T1 times the cosine of 25 degrees. And this side of the triangle up here is going to be T1 times the sine of 25 degrees. So now, and we've got the force of gravity acting downward down here. So write an equation which describes the forces in the x direction or horizontal direction. What do we have here? We've got T1 acting this way. What do we know has to be true? It has to be exactly equal to this component, the horizontal component of T1. So what can we write? We can write T2 must be equal to T1 times the sine of 25 degrees. What do we know has to be true about the vertical? Well, the magnitude of this one must be equal to the magnitude of this if this whole thing is 0. So in other words, the force of gravity must be equal to T1 times the cosine of 25 degrees. Let's see. Suppose the magnitude of that is 50. Determine the magnitude of T2. All right. So now they actually give us numbers. So what if this is actually 50 newtons? If you quick use your trig, you'll discover that the top is, this is equal then to 21.1 newtons. And this is equal to 45.3 newtons. That means we immediately can calculate a few things. Determine the magnitude of T2. Well, if this piece going horizontally that way is 21.1 newtons, T2 has to be also then 21.1 newtons acting in this other direction. this has to be that. And then what's the weight of the box? Well, Fg is acting downward. This is the only one acting upward. The force of gravity must be 45.3 newtons. And so the weight of the box is that. If we divide that by 9.81 newtons per kilogram, you'll discover the mass of the box then is about 4.62 kilograms. All right. So that's one example. And the other one I want to do is a ramp real quick with you. So for the ramp, the force is acting on it. It's resting motionless on the ramp, which means there must be friction. So we've got a force of gravity acting straight downward. Pretend that's not curved. My apologies. That should be straight there. We've got a normal force acting this way. And we have a force of friction, static friction, acting up this way. If we break this into components very quickly, just for our convenience to make it a little bit easier, if we take this one and break it into components that are perpendicular and parallel to the ramp, where this is a right triangle, this angle here is exactly equal to this angle here. And don't give us theta, so let's just call this theta. Wait a second, 20 degrees, it's right there. Sorry, it's hiding over there, my apologies. So theta is equal to 20 degrees, which means these two sides, this side here is going to be equal to Fg times the cosine of 20 degrees. And this side here, excuse my little drawing over here, is going to be equal to Fg times the sine of 20 degrees, given this right triangle, and Fg is the hypotenuse. Write an equation which describes the forces that act in the x direction. X direction in this case for ramps just means along the ramp. So in this case, what must be true? The force of static friction which is acting up the ramp must be equal to the component of gravity that's trying to drive this thing down the ramp. In other words, this component here must be exactly equal to this component here, or that piece here. And now, y direction just means perpendicular to the ramp. What must be true here? The normal force must be exactly equal to Fg times the cosine of 20 degrees. Oh, and now they give us numbers. And so now if the mass of the box is 8 kilograms, how do we figure out all the rest of this? Well, if it's 8 kilograms, that means our force of gravity, taking that times 9.81 newtons per kilogram, this is equal to 78.5 newtons. And if we break these two into their components, let's see here. Actually, we don't even need to solve this one. But if we solve this one then, taking that times the cosine 20 degrees, you'll discover that this side is 73.7 newtons. Oh gosh. Which means what has to be true about the normal force? If this component perpendicular to the ramp acting down is equal to that, this also has to be then 73.3 newtons. I think that may be my last example. Hold on a second. I can't go forward. Yep. All right. We'll save this for next time, although you can sort of figure out how to do it. You've got the rest of the period to work on worksheets 1, 2, and you can try a little bit of 3 as well if you'd like. Have a good night. Work on your homework. We'll see you soon.